3, Chapter 12, Chemical Kinetics. Rates of a chemical reaction. So first, let's talk about what even is chemical kinetics. We've seen a bunch of different reactions, know how to calculate concentrations, mass, different pressures. We know how to use stoichiometry in different chemical reactions. Now what we're going to look at is how fast a reaction actually occurs. So that's kind of chemical kinetics, the rate of different reactions and how they relate to the concentrations of reactants and products. So the rate of a chemical reaction is a measure of how fast the reaction occurs. If a chemical reaction has a fast rate, there's a large fraction of molecules that react to form products during a given period of time. If a reaction has a slow rate, only a relatively small fraction of molecules react to form products during a given period of time. Now, when we measure how fast something occurs, or more specifically the rate at which something occurs, we usually express the measurement as a change in the quantity per unit time. So a really good example of this is thinking of the speed of a car. The rate at which a car travels, we look at it as miles per hour. So we measure how quickly or slowly a car can go through finding the miles it can travel per hour. We report these rates in units that represent the change in what we are measuring, distance, divided by the change in time. So we have, if we were looking at speed, for example, we'd be looking at the change in distance over change in time, which we could also say change in distance, change in x, over change in time. So really similar to that, the rate of a chemical reaction is measured as a change in the amounts of reactants or products. We usually just define that as the concentration divided by the change in time. So, for example, if we were to look at this chemical reaction, hydrogen gas plus iodide gas makes 2 hydrogen iodides. And I would define this rate of the reaction in time interval. So I would say that my rate is equal to the change in concentration of my concentration at the final time minus the concentration of hydrogen gas, at initial time. And that would be over T final minus T initial, right? So it would be the change in the concentration at that final time over the change in the concentration at the initial time. Now, we usually don't write it like this because we know it's delta for the change of final minus initial. So it'd be delta H2 over delta T. So in this expression, you can see that the hydrogen is given a negative sign. I wrote a negative sign here. Now, why do you think that the hydrogen is at a negative sign? Look at where it's located in the reaction and what a reaction does. So the negative sign is part of the definition when we define the reaction rate with respect to a reactant. So a hydrogen is a reactant, and a reactant is disappearing as a product forms, right? It's not in equilibrium, it's a completely forward reaction. So as our hydrogen iodide forms, our hydrogen itself is going away. So for the definition of when we are expressing reactants, we always have the negative sign. Since the concentration of a reactant is going to decrease as the reaction proceeds, and the concentration of the products would increase as the reaction proceeds. Therefore, the change in concentration of a reactant is always negative because the reactant concentration is going down as the reaction moves forward. The negative sign makes the overall rate positive. By convention, we can report these as positive quantities. So really similar, you would write the change of rate, the rate for iodide, negative change of concentration of iodide over change of time. Now, we can also call this rate of disappearance because of this negative sign, because the concentrations of reactants are disappearing as the reaction proceeds. Now, let's write the rate for the product. Now, this is not going to have a negative sign. This is going to be positive, also known as rate of appearance, because the products are appearing and the concentration is increasing as the reaction moves forward. Now, one more different part of this is the fact that there's a coefficient in front of HI. So we have to include that. So we would say rate is equal to plus 1/2 change of the concentration of HI over change of time. Because product concentration increases as the reaction proceeds, the change in concentration of a product is positive. We define the rate with respect to a product. We do not include a negative sign in the definition. The rate is naturally positive because it's appearing as the reaction moves forward. The factor here is 1/2 in this definition, which is related to the stoichiometry of the reaction. In order to have a single rate for the entire reaction, the definition of the rate with respect to each reactant and product must reflect the stoichiometry of the reaction. It has to represent the entire stoichiometry. So basically, for this particular reaction, since we have 2 moles of hydrogen iodide that's produced for 1 mole of hydrogen and 1 mole of I2, we have to put each coefficient as a reciprocal to indicate one of each. The concentration of HI increases at this rate twice as much as the concentration of hydrogen and iodide. So basically, if I have 100 molecules of iodide per second, then 200 molecules of hydrogen iodide would form per second, as 100 of iodide would disappear. So in order for the overall rate to have the same value when defined with respect to any of the reactants or products, we must multiply the change in concentration by a factor of 1/2, because you're trying to be in one of each, trying to make it really consistent. So that's how you would write a rate of change of a reaction. Rate of a reaction. So this is written a little bit prettier over here. So again, these are my rate of disappearance. This is my rate of appearance. You can see that the reactants will always be negative because the concentration decreases as the reaction proceeds forward. The product will always be positive because the reaction is appearing as the reaction goes forward. And we know that hydrogen iodine increases twice as much as hydrogen and iodide will decrease. So therefore, we have to have the coefficients used here, the stoichiometric coefficients in the reaction, as 1/2 for hydrogen iodide. So if we consider the graph here on the left, it represents the changes in concentration for hydrogen, one of the reactants, and hydrogen iodide, one of the products, versus time. So you can see one of the reactants and one of the products, what it does in our original reaction over a given period of time. So we're going to examine different parts of this reaction. So the change in reactant and product concentration, looking at this graph. So just looking at the green line for hydrogen gas, the reactant concentration, as expected, went down, right? We would assume, and we already did assume, that it's going to decrease as the reaction proceeds forward. That's why we have that negative sign. And here in this diagram, you can see that, as expected, the concentration of hydrogen gas decreases with time because reactants are consumed in a reaction. Now, if you look at the red line for the product, what's happening to that? Does that fulfill what we expected? It does. It's going up. It's increasing. So they're not going the same direction, which we would not expect them to. The product concentration increases with time because products are formed in a reaction. The increase in the hydrogen ion concentration occurs exactly twice as the rate of the decrease in the hydrogen concentration because of the stoichiometry of the reaction being 2 moles of hydrogen iodides are produced for every 1 mole of hydrogen being decreased. And the way that I know that is you can see here, if you observe it, this is increasing twice as much as this is decreasing. So this is like 1, and this little dot is like 2. So we can see that it's twice as much. So then if we look at the average rate, so the average rate of a reaction can be used calculating the rate expression. So we know that the rate expression was the following. Rate is equal to change of your reactants over change of time. So we can calculate the average rate of a reaction for any time interval using our equation that you write here. So you can always write the rate equation for when you're given a chemical reaction. You can calculate it for anything specifically. We can calculate it for H2 because we know this reaction and we have some data from a graph. So basically, for example here, if you were given the information that the change in the time intervals and change of concentration. So the rate in the average time interval given at between 10 to 20 seconds, for example. So if we looked at 20 seconds, right, and then 40 seconds, what you would do is you would look, okay, where is that for hydrogen? Okay, that's around like 0.6 something. And then where is it for hydrogen at 40 seconds? That's around 0.4 something. So then you would plug that in to find the rate. You would say, okay, negative is equal to change of my final would be for let's just say that's 0.45 molar minus 0.65 over, and this is molar, over 40 minus 20. So then the rate is equal to 0.20 over 20 meters per second, which then if you plug that into your calculator, you would get around, a calculator, 0.01. And again, this negative wouldn't be in your final answer because it's only part of the definition. So we just know that that's the rate for how much the hydrogen is disappearing in that specific time interval. And this could be done as many times as you want for when you're given specific data of different concentrations and different times. Now, whenever you're given all of the concentrations and all of the time intervals, you can always calculate the rate of hydrogen, the rate of iodide, the rate of the product. You just have to be given the information so that it's just change of concentration over change of time. So, if we look at the instantaneous rate, so the instantaneous rate of a reaction is the rate at any point in time and is represented by the instantaneous slope of the curve at that point. So we can determine the instantaneous rate by calculating the slope of the tangent line of the curve at that point of interest. So in our graph here, you can see that there was a tangent line drawn for both hydrogen and hydrogen iodide at 50 seconds. So you can see right here at 50 seconds, there was a tangent line drawn. And now we can calculate the instantaneous rate at 50 seconds as follows. So for example, we know that rate is negative delta H2 over delta T. And so now I can see that at 50 seconds, right, my change, because I'm calculating my slope, so this is my line, right? So my change would be the concentration of the difference of the height, which would be my molarity, so negative 0.28 molar over 40 seconds, which then becomes 0.007 meters per second. Again, just calculating the height difference. So you would make your tangent line like this, and then you would kind of go and figure out at what point that is to figure out the height difference. And it's negative because it's going down, which it would be negative here as well because it's going down. So that's how that negative goes away, just to re-explain that. So the negative always automatically goes away, but when you're writing it, you have to include it because it's part of the definition for reactants. So then if we look at for the hydrogen iodide, rate is equal to 1/2, positive 1/2, change of hydrogen iodide over change of time. And for hydrogen iodide, it's all the way up here. So again, you would find your difference in height. You would just find your slope, and that would be 1/2 0.56 over 40 seconds, and that would equal 0.007. So again, you just find the point. So the instantaneous rate is the rate at that particular point. So what's the rate at exactly 50 seconds? And since the plots are a curve, you take the tangent line at that point. And then what you do is you're trying to find the slope. Well, we know that slope is equal to rise over run. So that means the molarity change over time change. So then you just find the rise over the run for that point specifically of your line, and then plug that into your rate equation to find the exact instantaneous rate. So exactly as we would expect, the rate is the same, whether we use one of the reactants or the products for the calculation, because they're all equal to each other, right? This is exactly what we expected. Notice that the instantaneous rate at 50 seconds is 0.0070, and it's between the average rates calculated that can be calculated for different rates for 40 and 60, for example. So it should be at 50 seconds in between what the rate should be at 40 or 60 for hydrogen or iodide. So for a generic reaction, the reaction rate can be defined as the following. So here we have a really generic reaction. You have your reactants and your products and the coefficients. And then you can see that you can write rate is equal to negative 1 over A, so it would be whatever coefficient, change of concentration of one reactant over change of time, is equal to negative 1 over the coefficient, change of the reactant over change of time, which is then equal to positive 1 over the coefficient for that product, change of product, concentration over change of time, and equal to, if there's another coefficient, it's always positive, 1 over that, change of concentration of product over change of time. So again, you don't necessarily always have 2 reactants or 2 products. You could have 1 reactant and 1 product, you could have 2 reactants and 1 product, or you could have 1 reactant and 2 products, etc. But the definition is always the same. The reactants are disappearing as the products are appearing. It's change of concentration over change of time. And we always have the reciprocal of each coefficient because they have to equal the same. As one appears, the other one is disappearing, and vice versa. So from the definition, we can see that knowing the rate of change in the concentration of any one reactant or product at a point in time allows us to determine the rate of change in the concentration of any reactant or product at that point in time. However, predicting the rate at some future time is not possible for just a balanced equation. So with that said, let's do a problem. So imagine you have this balanced equation. In the first 10 seconds of the reaction, the concentration of iodide ion drops from 1 molar to 0.868 molar. calculate the average rate for this reaction in this time interval. Okay, so then since I'm interested in iodide, I would just write my rate for iodide, which would be rate is equal to negative 1/3 change of concentration of iodide over change of time. What am I solving for? Calculate average rate. So I'm solving for this. So I have to plug in, I have to make sure I have time and concentration. Well, I have concentration and I have time because it's saying in the first 10 seconds. So it's 10 seconds from 0 basically. So then I have 0.868 molar minus 1. Now, does it make sense that it went down? Because 0.868 is less than 1. It does because iodide is a reactant. Again, you'll always end up getting a negative, so your negatives cancel out. You should not have a negative rate when you're doing any of the reactants or the products. When you're doing the change of the concentrations of the reactants, they should always be negative, which then cancels out with the negative of the definition because the reactants are disappearing, so it should go smaller. Over 10 minus 0 seconds. And that will equal 4.40 times 10 to the negative third meters per second. Awesome. Now, determine the average rate of change in the concentration of H plus hydrogen ion during this time interval. So, what's my rate for hydrogen? Minus 1/2 change of hydrogen ion over change of time. So I wasn't given the concentration for hydrogen here. How can I figure out the rate of hydrogen not knowing the concentration change? Well, let's go back and figure out exactly what we know for rate. We know the rate of the overall reaction. We know that rate would equal negative change of, I already have negative here, change of hydrogen peroxide over change of time is equal to negative 1/3 change of iodide over change of time, which is equal to negative 1/2 change of hydrogen over change of time, which is equal to positive change of I3 minus over change of time, which is equal to positive 1/2 change of water over change of time. So, sorry, that's really messy over there in that last bit. We know the relationship between iodide and hydrogen, and I just solved for the rate. So I know that this right here is equal to 4.40 times 10 to the negative third meters per second. So if I were to find the relationship between iodide and the rate, I know that, well, the rate is equal the same for all of them. We just have to take into account the coefficient. So this is my rate here, and we know this because of the 1/3. So when we're trying to find the rate for hydrogen, we have to take into account the 1/2. So basically, 4.40 times 10 to the negative third meters per second is equal to negative 1/2 Now, again, you're looking for average rate of change, so not a rate, so this can be a negative number. So you would have to multiply this by negative 2 on both sides, which then gives you negative 8.80 times 10 to the negative third meters per second is equal to the rate of change of hydrogen ion. Again, when you have concentration over time, it's a rate of change. If you're just looking for rate, you're looking for a positive number. So it's showing you 2 different ways of calculating that. Let's do another practice problem. So determine the average rate of change of B from the time interval of 0 to 302 seconds. Given this table below, you're going from A to B. So I'm going to give you a little moment here to try this on your own. So what do we know? Well, we know that we have all the information given for A, right? So I know rate of A is equal to negative change of concentration of A over change of time. So then the rate is equal to, if I'm going from 0 to 302, I'm going from negative 0.160 minus 0.720 divided by 302 minus 0. So then my rate is equal to 0.00185. So 0.16 minus 0.7 divided by 302 is would be negative, and then the negative cancels out, so 0.00185 millarity per second, not meters per second. So we know that rate is equal to the change of concentration of A over change of time, which would equal positive 1/2 change of concentration of B over change of time. You're looking for average rate of change of B, so you're trying to solve for this. So then we know that we solved for the rate. So then we can say that the rate is equal to 0.00185 meters per second is equal to positive 1/2 change of concentration of B over change of time. So then to just figure out the rate of change of the concentration of B and time, we would multiply both sides by 2. So then the average rate of change of B would be 0.0037 meters per second. So you always have a lot of information by just knowing your rate equation. All right, moving on from that, talking about last little bit for this section of how measuring reaction rates in real life. So in order to study the kinetics of a reaction, we must have an experimental way to measure the concentrations of at least one of the reactants or products as a function of time. Now, it's not as easy to just look at a reaction, put two different aqueous solutions together, and determine the rate. If there are two clear solutions, how can we actually visualize the change? So we're always looking at light difference when it comes to chemical kinetics. So the most common way to study kinetics of a reaction is through spectroscopy. The reaction, for example, of hydrogen iodide from hydrogen iodide, if we go back to this reaction, if everything was clear and we watch this reaction, how can I see the difference over time? So we're always looking for spectroscopy, which you can see this little setup down here, and I'm going to explain it in just a second. So if we go back to the original equation we've been talking about in this lecture so far, the reason this reaction can be studied through kinetics is because of color. So iodide is actually the color violet, and hydrogen and iodide are both colorless. So as iodide reacts with hydrogen to form hydrogen iodide, what happens is, since iodide is a color and everything else is colorless, and we know that the reactant begins to disappear, what do you think will happen to that violet color as the reaction moves forward? It will fade, right? Because we know the reactant is disappearing. So as the reaction moves forward, the violet color of the reaction begins to fade. So what we can do is we can monitor the fading of the color. We can visualize the time as how long it takes for that color to begin to disappear. And we know once it's colorless, we've reached our end goal. So we can monitor the fading color with a spectrometer. And a spectrometer is a device that passes light through a sample and measures how strongly the light is absorbed. So here in my little diagram below, if the sample contains the reacting mixture, the intensity of light is absorbed through the mixture. So the intensity of the light absorption will decrease as the reaction proceeds, providing a direct measure of the concentration of iodide as a function of time. Because light travels so fast, and because experimental techniques can produce very short pulses of light, spectroscopy can be used to measure reactions that happen on timescales as short as several femtoseconds. So you have your light source, you have your slit, you have your monochromator, which is just basically a prism. And all that does, it goes through our little cuvette with our sample. So this is our reactant mixture. So then it goes through this detector, and then we can see the different intervals as time goes through. And we know that it's going to go decrease because the color will fade as the reaction is moving forward. So we can actually find the absorbances over time. Now, we already know from Beer's law how absorbances relate to concentration. So we can apply that to then find the difference of concentration over time and measure the rate of a reaction. Now, by measuring changes in pressure, we can also monitor reactions in which the number of moles of gaseous reactants and products change as the reaction proceeds forward. So if we consider this reaction of dinitrogen monoxide that's reacting and forms nitrogen and oxygen gas, you can see from the balanced chemical equation that for every 2 moles of dinitrogen monoxide that reacts, the reaction vessel contains 1 additional mole of gas. As the reaction proceeds and the amount of gas increases, the pressure steadily rises, right? So because you have a higher mole, you have 3 moles of products, as this goes down, you know that the pressure will increase as the reaction moves forward. So we can use that rise in pressure to determine the relative concentration of reactants and products as a function of time. So this is another way to measure a reaction rate. Very common way and most used is the light determination through spectroscopy, but can also be used through pressure. So we can use all of the 3 techniques mentioned here. So we have spectroscopy and the pressure measurement, and another way to measure pressure is through something called polarimetry. So I'm going to measure that here. Write that here. Polarimetry. And that is measured in the following way. So, for example, experiments were done in the past where the rate of the conversion of sucrose to glucose and fructose was discussed. So, sucrose's ability to rotate polarized light is the way that these experiments are done. Now, polarized light is light with an electric field oriented along one plane. So when a beam of polarized light is passed through sucrose solution, the polarization of the light is rotated clockwise. In contrast, the products of the reaction, which would be glucose and fructose, rotate polarized light counterclockwise. So sucrose would go clockwise, and the products of sucrose go counterclockwise. By measuring the degree of polarization of the light passing through the reacting solution, scientists can determine the relative concentration of the reactants and the products as a function of time. So measuring reactant rates are done through polarimetry, spectroscopy, and pressure. Now, spectroscopy is the most common one, I would say, because it's very, very attainable and easier to see the difference of light through time, setting up a spectroscopy experiment. Some reactions occur slowly enough that samples, or also known aliquots, can be periodically withdrawn from the reaction vessel and analyzed to determine the products of the reaction. We can use instrumental techniques such as gas chromatography, which is the diagram here below, or mass spectrometry, as well as wet chemical techniques like titration to measure the relative amounts of reactants or products in the aliquot. By taking aliquots at regular time intervals, we can determine the relative amounts of reactants and products as a function of time. Now, that's only possible when the reaction is very slow. So these first three techniques are for faster reactions. When a reaction is happening slow, I can take a chunk of that reaction, for example, and titrate it. Or I can use gas chromatography to figure out the reaction. Now, this again is only possible when you have a very slow reaction. If you have a fast reaction, it's very, very not attainable to be able to take samples and measure it. You would have to have the reaction happen and you're set up to be taking information the entire time. So different ways of measuring reaction rates.